hit record. So I'll start now. Let me just share my screen. Yeah. Full screen. Full speed come. Full speed. Okay. Good day, everybody. All of you are in different parts of the world. Let me introduce the seminar series and its objectives. So, Critical Transitions in Complex Systems seminar series is being jointly hosted by IIT Madras in India and PIC, Potsdam Institute for Climate Impact Research in Germany with Professor Jürgen Kurz. This seminar series brings together experts from various fields such as climate science, mathematics, neuroscience, fluid mechanics, etc., and aims to disseminate the state of art in the prediction of critical transitions in these diverse fields of study, and more generally nonlinear dynamics and complex system theory. The seminar series takes place every month on the last Monday. So please mark your calendars. Before I introduce the speaker, a few housekeeping items. I request everyone to turn off their microphones and please use the Q&A box in Zoom to ask questions to speakers. There will be time at the end when the speaker will answer the questions. And now let me introduce today's eminent speaker. Professor Michael Small is a CSIRO UWA Chair of Complex Systems and hold academic positions at the University of Western Australia with CSIRO, that's the Australian Government Research Agency. He's the Deputy Editor with Chaos and Main Editor at Physica 8. Michael's research interest is in nonlinear dynamics, nonlinear time series analysis, complex systems and networks. His work spans a range of application areas and focuses on data-driven methods for understanding complexity and chaos. Applications which is currently working on include traffic modeling, mineral exploration, mental health, and disease modeling. Today, Dr. Small will speak about the importance of embedding lag and how to choose it. So the floor is all yours. Let me stop sharing. Yeah.
Thank you, Sujit. And I'll just start sharing. Hopefully you can see that now.
Yes, it's come. Thank you.
So thank you, first of all, for the invitation to speak at this seminar series. And it's really an honor looking at the previous speakers in the series, really experts in the fields and made some great contributions to this area. What I'm going to be talking about is quite an old problem. And in some ways it might seem kind of a little bland and technical, but I hope that you'll see that there's important work to be done in trying to get embeddings right, and that it has some payoff for modeling different dynamics and particularly modeling tipping points. So this is, as Sujit said in the introduction, my position is at the University of Western Australia, but also with the Australian Government Research Agency, CSIRO. With CSIRO, I'm looking at applications of these techniques for geological modeling. So for understanding subsurface geology and geological processes in general. And we're also doing some work jointly with a research centre funded by the Australian government and different companies in the resource sector to try to look at applications of nonlinear time series techniques for problems in maintenance. So this is predicting when things fail. Okay, so first of all, this work is everything I'm going to talk about tonight, this morning, is work that is in a recent paper that we published in Chaos, which is partly a review and partly some new work. It's work led by my student Eugene Tan, so this is a part of his PhD, and it builds on work of my research group at UWA. So throughout the talk, I will be talking about a lot of work of other people, and the references to that work are primarily to be found in this paper. So first off, just a little bit of very fundamental background. So I think for everyone here, we're familiar with the idea of a dynamical system. and that being some map from some set, which will be in general Euclidean space or some subset of it, M, and with some time function, so that I have some operator phi which will map my state Z forward by some time t. So the details of this is not so important, but the thing that is interesting and directly important for what I'm talking about here is that we're looking at reconstruction problems. So we have a dynamical system, we have some evolution operator, some phi, which governs how things move, but we don't know what that phi is, and we can't observe the state of the system, the Zs, directly. We can only observe some measurements from those states. So we have access to the output of some measurement function H, which is mapping the points in this space M forward to R, and it's R that I observe. Okay, so yeah, if I could turn the annotation off. Yeah. Not very useful. Sorry, let me go back and get rid of that. So the basic result, which is from 1981, the Tarkin's embedding theorem basically tells me that provided I've made these scalar observations of my dynamical system, so my output of my measurement function, a sequence of xi's, a time series, then if I want to reconstruct generically the underlying differential equations, then I only need access to those xi's, and I can take successive lagged values of them, xi plus 1, up to some number of these values m, to construct a sequence of vectors, which I'm going to call vi, and these sequence of vectors give me the dynamics. Now, Tarkin's proved this for smooth manifolds, and the result is largely topological, so that most of what he said is not actually about diffeomorphism between vi and the dynamics, but a homeomorphism between the actual objects. This was extended in the wonderfully named Embeddology paper of Sauer, York, and Castagli to the case where you have a fractal attractor, which is obviously for chaos the cases that we're most interested in. Now, okay, so all this is ancient history. The picture, and I apologize for the amateur nature of the picture. I hope it conveys the message. The picture of what we've got is on the left here, we've got some manifold M, that's the blue set. We've got states Z, which are moving under some evolution operator phi t. And we can just measure out via some function H, a sequence of xi, which gives us the time series you see in the top right-hand corner. Now, that time series, we perform an embedding and we get a set of points, the vi down the bottom right, which are, according to Tarkin's theorem for a smooth manifold, homeomorphic to the original object, and according to the extensions, diffeomorphic to the dynamics on the attractor. Another way of thinking about this, just pictorially, for everyone's favorite system, the Lorenz system, if we're just going to observe a time series from that, you see down the bottom, then some time delay embedding process, which I'm going to be able to take that time series, and just by looking at lagged components of the x coordinate, because that's all I've observed through my observation function, I get something which is equivalent through some diffeomorphism to the original dynamics. So the reconstruction has everything I need to understand the dynamics of the system. Okay, so that's all the theory, and the theorems tell me that guarantee that I can do this generically, which means there's some conditions on when I can actually do it, provided my H function is smooth, provided I've got enough data, provided I've got observations frequently enough, and provided there's no noise. So there's extensions to these embedding theorems that deal with some of these problems, but the problem that I'm going to be looking at is how to extend this basic embedding idea that I'm going to take XTs and turn them into VTs that are vectors based on lagged versions. That the original theorem just says, just take successive values. Now in practice, that's going to work, but maybe not going to work as well as alternatives. In general, I might want to think about taking different lags here, L1 through LM, that somehow capture the dynamics. Or I might just take the easier case, which is what I'll start talking about today for today's talk, and have successive values separated by some time lag tau. So this is the embedding lag. It's the distance between these coordinates that I'm using to reconstruct the dynamics. And so what is a good choice of tau is the basic question of this talk. Way back in history, if you go back to when people started doing these sorts of things in practice, there's several rules of thumb that popped up in terms of choosing tau, and each of them is based on some version of the idea that you want coordinates that are separated far enough that xt and xt minus tau are different, but not separated so far that xt and xt minus tau are completely independent of one another. So if tau is too small, xt and xt minus tau are going to look very similar, and you're not going to get much additional information from xt minus tau. If tau is too large, then A, you're using too much data, and B, xt and xt minus tau are just completely independent of each other. So one might try to look at autocorrelation and look for when that is first approximately zero, like the minimal value of tau that autocorrelation drops to zero. We might try the nonlinear version of this and look at mutual information. So you can see the way that I've written it here, with mutual information being a probability, joint probability marginalized by the independent probabilities of each of the events. It's just the nonlinear version of autocorrelation. It's how much information do I learn about xt from xt minus tau. Now, in the special case that your signal is approximately periodic, one, and my favorite way of doing this, is just to take a quarter of the period. You can see straight away that if I choose a quarter of the period, then this is going to be, for a signal which is approximately periodic, about the same thing as the first zero of the autocorrelation, and about the same thing as the first minimum of mutual information. So that's kind of one way to estimate embedding lag, and that's kind of the way that in practice it gets done a lot. That is sufficient if you have a low dimensional system that's strongly periodic and has one dominant frequency. It's also sufficient, particularly if you're just estimating invariance, perhaps not Lyapunov exponent, but correlation dimension and other related quantities. It's maybe not the best choice as a more general modeling problem. So these first ways of estimating the embedding lag are all based on some sort of premise about trying to choose a characteristic time scale in this Goldilocks zone. So you want lags that are separated far enough that the xt and xt minus tau are different, but not separated so much that xt and xt minus tau are completely and irrevocably independent of each other. You may have seen the idea of false nearest neighbors, which is widely used for estimating the embedding dimension, the M, and the idea behind characteristic length as a choice of embedding lag, tau, is that one does the same sort of thing. So you're choosing an embedding lag such that, now we're going to measure the false nearest neighbors here by looking at the addition of we're looking at points Vi and Vj in our embedding space, and we're looking at the successors of them after some time k. So are they still close? Do they spread out? How much do they spread out by? And we want to minimize this quantity now for our choice of both embedding lag and embedding dimension. An interesting variation on the same theme was proposed in 91, and this basically takes an ordinal kind of view of things. So if I take a point Vi and I look at its neighbors, and I see where those points go to after time k, so the neighbors of Vi plus k, are they in the same order relative to Vi plus k as they were relative to Vi? So if you imagine the points starting off close together around Vi, do they spread out in the same way, or do they get mixed up somehow? And we want a good embedding to be one where we retain as much smoothness as possible here. There's extensions of these based on other geometric principles where we're trying to spread the points out in space, or try to provide embeddings that perform prediction well. But you'll notice that the methods here are all now dealing with the problem of estimating not just an embedding lag per se, but a sequence of lags that performs well for some idea of reconstructing the dynamics. We're assuming the dynamics is somehow smooth, and we expect to see that in the reconstruction. So whereas the first techniques are all just based on trying to find a sweet spot between too large and too small, these methods are trying to build and choose an embedding lag or group of embedding lags that provides a good approximation to your dynamics. Now, where things get interesting is when Lou Pecora and colleagues extended this idea for looking at basically applying a version of continuity. So they argued that if I've got a sequence of embedding lags, L1 or L0, which is 0, L1, L2, L3 up to Lm, and I want to add a new embedding lag, Lm plus 1, then I would hope that these embedding lags, the set of lags L1 to Lm plus 1, are functionally independent. What that means is that xt minus Lm plus 1, if I try to write that down as a function of the other lags, then that will fail, right? If my new lag coordinate is a simple function of my other lag coordinates, then that means that I haven't added new information by adding that additional lag. So I want functional independence. I want this function f that I've written down here on the right-hand side to not exist, or to be difficult and complicated. In other words, I want f to not exhibit smoothness. Smoothness here is going to be quantified just by looking at the basically the epsilon delta definition of smoothness. So in the picture on the left, if I take a neighborhood of a point in my first L1 to Lm embedding lags, and I take all the points that are in within some range delta of that, and then I look at the additional coordinate, the new lag, and I apologize, the picture's got tals rather than L's, but that's simply because I pulled this from the paper, from my paper with Eugene, and I've changed the notation here. But if I take my points, my first coordinate, keep those points within a ball delta, and I look at which of the additional coordinates are within a ball epsilon of my new point xt minus Lm, that gives me my measure of smoothness. The more of the blue dots that maintain closeness to the red dot in the new coordinate, the smoother it is. And the worse that lag choice is as an additional coordinate for my model. I want to choose the one which is the least smooth because it's got the most information, it's got the most complication. Now, there's a kind of complicated technical extension to this, which essentially says that, well, this all depends in a complicated way on how far ahead I'm predicting and how big a ball I choose. And in fact, what I should do is average out these things to get a smoother and more reliable measure. And that's essentially what the Kramer paper of 2021 did, using this L statistic, which was proposed by Uzal in 2011. So the technicality here is essentially in the first equation that I'm going to average this quantity over embedding lags, but essentially think of this just as an additional bolt-on onto Pecora's continuity idea. So it's to make the same idea more robust, and Kramer decided to call this the Pecozal algorithm, which is obviously Pecora and Uzal concatenated. So this method is now a full attempt to get sequentially a set of independent and distinct lags to build a model under the proviso that my coordinates are as different as possible. So there's a functional continuity-based definition of what I want in my good choice of lags. And a second method applies a similar sort of idea. MDOP is for maximum derivatives on projection. And the idea here is that you take the directional derivative and you look at the directional derivative you get when you add a new coordinate, and you want that to be as maximal as possible because you want the F, the same F that Pecora was trying to get as complicated as possible. You want that F here to be as large as possible. So it's the same sort of idea. But rather than focusing on continuity, it's focusing on trying to make the derivatives, focusing on measuring a property of the derivatives, but again, to get sequences of lags. Okay, and finally, I had to mention this one because it's my own. It comes with a great big, long, complicated formula, which I won't explain in detail. But it also achieves the same sort of thing. So what it's doing here is trying to find an F that, okay, it's not an F here. The F here is not trying to make the individual coordinates as independent as possible. The F is trying to build the best predictor of the next component from the previous components, right? So the best choice of lags is the set of lags that gives me the best model. And the detail on the slide here is describing how you might do that in a formal way to achieve a regularization where you just select a subset of the lags. So if I'm going to look at xt plus 1 as a function of f of xt and all the preceding values, I really want to select a subset of those xt minus L0, L1, L2, up to Lm minus 1. And we can do that through a subset selection process, and we can measure the performance of this with something like, in this case, description length. But essentially, it's the same kind of general idea as both the Pecozal method and the MDOT scheme on the previous page, in that the model that performs well from those lags to predict the next one will be on a set of coordinates that are as different from each other as possible. Okay, now I'm now going to ignore this scheme of building a model the way that I'm describing here from that I did in 1999. I'm going to look instead at the more recent and more elegant approaches of Pecora and also Nechadi's method, and compare them to the new method, which is going to be what I propose in this talk. So we'll come back to these schemes as comparisons to what I'm going to show you now. But what I want you to have taken from what I've shown you so far is a progression from schemes to select an embedding lag tau, which essentially are looking for a Goldilocks zone, to schemes that are selecting a group of different lags based on criteria for building models that have good generic properties in terms of continuity or independence or maximal structure. And our approach is to build models or to choose embedding lags such that the embedding itself has the nicest topological structure, I guess, is the way to say it. And the way in which we measure this is using the framework of persistent homology. So persistent homology is or topological data analysis, more correctly, is a computational scheme to compute homology of clouds of points. So what you see here is a group of points, and I'm putting a ball around each point. Those balls are radius delta, and I'm letting that radius delta grow from left to right, larger and larger. The object that I'm interested in is the cloud of points, if I think of those points as nodes, and the edges between those points that are defined to exist if the two balls intersect. Right. So on the leftmost picture, I've got 1, 2, 3, 4, 5, 6, 7, 8 discrete points with 8 balls around them, and none of them intersect. So I've just got 8 isolated dots. This is reflected in the notation at the top. I've got beta naught and beta 1 are the Betty numbers, Betty naught and Betty 1. Betty naught is 8, saying I've got 8 components. As I make those balls bigger and I move to the second picture from the left, I now 2 of those points join together, so they're now connected, and I've now got 7 separate components in my graph. And so Betty naught is 7. Betty 1 is counting the number of holes in this graph, and that's still going to be 0. But as I make these balls bigger again, I get to the point where the individual dots are now all connected together in a kind of ring shape, and there's a hole in the middle. So both Betty naught is equal to 1 because I've got 1 connected component, and Betty 1 is equal to 1 because that connected component has a hole in it. What I mean by a hole here, more technically than I'm drawing it, is defined in terms of the simplicial complex and its boundaries. Right? So the simplicial complex has a void in the middle of it, and that's what Betty 1 is counting. As I make the holes get bigger further, the balls get bigger again, the graph becomes fully connected, and so the simplicial complex becomes complete, and there is no hole either. It's just one single component, but everything connected to everything. Okay, so what I'm going to be interested in is small segments of trajectories. And what the problem I'm going to be looking at is when those small sections of trajectories exhibit shapes that look like circles, because we've got some sort of periodicity, we've got some sort of repeating behavior in the dynamics. So I want to see holes, and I want to see those holes persist for a long range of different values of delta. Right? So the computational machinery of the topological data analysis gives me a way of measuring all of this. And the recipe basically is described here. So I choose some time tau. I then do a 2-dimensional embedding. So I look at xt minus tau. And I don't do this for I do this for the entire time series, but then I subsample strands of that time series of length 4 tau. Right? So if I'm choosing tau to be a quarter of a period, I'm choosing a whole bunch of small, short strands that should be something like the approximate periodicity of the time series. And then for each of those short strands, I apply the topological data analysis techniques to determine whether a hole exists, and if so, for how long it persists. So do I see the emergence of these hole structures like this? And if they appear, for what range of radii do they persist for? The larger the range of radii that they persist for, the more likely that these structures are not due just to noise. You could imagine that if a hole appeared and then disappeared only for a very small range of these values of delta, and delta are just it's a real scale on the embedding space. So it's a measure of size in the embedding coordinates. If it's only a small range of deltas that exists for, then it's a fragile structure. If it exists for a large range, then it's more robust. And then I just record for each of those strands that I've chosen at random, the range of delta that it persists for, if that exists, and that is what I call the persistence. That's my first quantity. And here, just showing roughly, and yes, very roughly, pictorially what's going on. So I've got a time series up the top, and I've identified a length tau, and I've pulled out from this time series sections of that of length 4 times tau. Each of those gives me a series of dots, which on the one on the left doesn't exhibit a hole, so its persistence is 0. It doesn't persist at all. May exhibit a hole that persists for a short time, or may exhibit a hole that exists for a long time. And so I record the length of time that each of these holes exists for, and that's for each of those strands that I've selected at random. Now, armed with this measure of persistence of the topological structures, I can now move on to try to explain to you what it is that I'm trying to achieve by using this as an embedding technique. If I think about, as an archetype, simple dynamical systems like Lorenz or Rossler, these things go around in circles. And if I've taken these strands, then they're going to approximately be orbits of those systems. And I want those orbits to look like the thing on the top right, because these points are arranged in a circuit, in an orbit, so they do, in the embedding space, reflect the orbital nature of the data. I would prefer the circle over the ellipse because the points are spread out more. I would prefer the circle without the tail to the circle with the tail, because I'm using these points as efficiently as possible. And I would prefer something where the points are spread out as much as possible and not wound tightly around, as in the bottom left-hand corner. So I now am going to propose 2 ad hoc measures for what I call circularity and efficiency, alpha and gamma, and use that to compute my performance criteria, which is how well the embedding lag works. And then I'll finally bring all this together and show you how that works in practice. So the first part, the circularity for a given strand, so my given piece of an orbit, I identify if it does have a hole, and if that hole is persistent, find the most persistent hole, find the points on the boundary of that hole. So that's what's reflected in the illustration going from the top to the bottom. The bottom, I'm only interested in the points that are on the boundary of that hole. And then take those points and basically measure the roundness of them as a cloud of points by taking the first 2 principal components of that cloud of points and looking at the ratio. As that ratio gets closer to 1, it's more circular. As it gets smaller than 1, it's more elliptical. Okay, that's my first measure, circularity. My second measure, the efficiency, is how much of a tail I have to deal with. And here I just simply compare the area that I get from the boundary of the hole. So again, the same set of points, that gives me the A sub H. And I compare that to the smallest convex polygon that I put around all of the points, that's APC. So if I want to bound the entire set of points versus bounding just the piece of the orbit corresponding to the circle, what is the ratio of those 2 areas? The closer it is to 1, the less stuff I've got hanging around the tail. So these 2 ideas are going to be what drives my measure of how good an embedding is. I want to see these sampled strands that are as circular as possible and are as complete as possible without little bits hanging off the edge. And so it's an ad hoc measure, but it's a measure which is trying to build the topology of the embedding in such a way that the points are spread out amongst themselves as much as possible. Okay. So I hope you're still with me. And now I'm going to bring all this together and show you just how that actually works in practice. So just for the sake of comparison, I'm going to take 3 different time series, 2 artificial ones and 1 genuine experimental time series. So just a sum of sine waves of different frequency, the standard Lorenz system, and a spiking neuron from a lobster crayfish. This is data from the group of Henry Abarbanel from some experiments that they did back in the 90s, I believe. They shared the data with us, and essentially this data is interesting. Apart from being experimental, and apparently chaotic, it also has this kind of multi-scale behavior. So you've got these high frequency bursts with a non-constant period, and you've got long diversions in between those bursts. So it's the sort of data which is extremely challenging to successfully embed with most techniques, because the idea of what do you mean by time lag, if you're going to pick a single time scale, becomes very complicated here. Now, with these 3 time series, I'm going to compare the 3 methods that I've introduced. The method, our new method based on this combination of making things look like circles and using the data as efficiently as possible. This we call stops. The Vercora/Uzal algorithm, which is based on looking at embeddings where if I build a function between the components, it's as continuous as possible. And Nejuare's MDOT algorithm, which is based on a combination of ideas from information theory and expansion of directional derivatives, so maximizing the directional derivatives to make your system as expansive as possible. Okay, so what I'm showing here on the top plot is first up. Okay, so the x-axis in every single panel is the time lag. This is for the sum of sines signal, so it's a bunch of sine waves at different periods. The periods of the sine waves are actually shown as the solid blue bars in the bottom 2 plots. Right, so there's 3 sine waves, 1 period 5, 1 period about 50, and 1 period about 250 in the time units that I have here. The first line at the top, that's the mutual information. So it's the standard mutual information. We might expect, if we were to choose a time lag from that, we choose a time lag at the first minimum of it. And you can see that there's several minimums corresponding to the different frequencies and combinations of those frequencies. But it's not, apart from giving us numbers at different scales, it's not completely useful. The second panel is that persistence measure that I introduced first. So that was just how long do these holes persist for as a function of embedding lag. The third and the fourth panel are the ones that are more interesting. And so the fourth panel is the variance. The third panel is the mean of the same properties. So in both of them, the black line, the red line, and the blue line are our measure of how circular things are, how efficient things are, and the product of those two, which is my proxy for a goodness of the embedding, just by multiplying these 2 quantities that I both want to be high. The third panel is the mean of that quantity. The fourth panel is the standard deviation. And for comparison, the green and the red are the predicted time lags that the Pacuzol and MDOT algorithm come up with. So in summary, both Pacuzol and MDOT give you a short lag, and then they give you other different lags that are all over the place and nowhere near any of the features of interest. The significance measure, our combination, gives lags that are similar to both of the other 2 measures, but again, it's not clear that any one of these algorithms is performing any better than any of the others. And it's also not clear that any of them is really capturing the true 3 time lags that we expected. Perhaps I would say that there are peaks in the black significance curve closer to the peaks of the true frequencies compared to the alternative methods, but it's certainly not clear cut. This is the same calculation for the Lorenz system. I don't have the characteristic timescale shown here because it's not mechanically constructed as a series of sine waves. I do have in the first panel is the mutual information with a minimum at about, what was that, about 80-ish in the units that I'm computing here. Because identifies a lag at a similar value and a lag at a smaller value. MDOT is nowhere near that. And the significance measure pretty much lines up with both Pacuzal and the mutual information. So it's performing similarly, but no better. The third one is the time series of the Lobster. And you can see immediately the mutual information is not useful here. It's just decreasing. It's just not coping with the multiple timescales of the system. The Pacuzal and MDOT algorithm kind of go berserk, really. They're selecting a whole bunch of different time lags, very many of them all over the place. As I said, remember the signal is both it's noisy, but it's also got both a very long period of quiescence between the little bursts, and the bursts are also of non-constant frequency. So it's an increasing or decreasing frequency of spiking. The significance measure, our proposed measure, does seem to capture these peaks at about the same place as the dominant peaks from Pacuzal, but after that isn't quite so enthusiastic as the other 2 schemes of suggesting lots and lots of time lags, which, if we could use that to embed this data in 3 dimensions, would be a bit of an advantage. And so here I'm showing you just that. Forgive me for the picture, which I've put on the side I've rotated it through 90 degrees to try and make it more easy to see on the screen. So the top row is the embedding I get with the lag suggested by Pacuzal, with the MDOT in the second row, and with our new algorithm in the third row. And what I want to draw your attention to is, well, so first of all, the characteristic shape of the embedding of this data is that you've got these spirally bursty bits along the bottom of each panel and along the right-hand side of each panel. And then you've got the quiescence along the top and down the left-hand side. So you've got long sort of laminar periods along the top and the left, and then you've got the loopy stuff down the bottom and up the right-hand side. And interestingly, only the new algorithm, STOPS algorithm, constructs an embedding which captures the appearance of the loopiness by selecting a short lag. Both Pacuzal and MDOT just select large lags, which just capture the large scale behavior of the system without really embedding to model the small scale structure. And what this means is that when we go to build models of this, and this is kind of the main point, is if we try to use these methods to construct lags to build a model to understand the dynamics, then the models that we're going to get out from this new algorithm much better capture both the short-term bursting and the changing frequency of the short-term bursting compared to the standard algorithms, which do a poor job capturing the spiking regime and merely capture the long-scale dynamics. This plot is a concatenation of 10-step free-run predictions, which is why the amplitudes in all of the embedding models is smaller than the amplitude in the data. It's a reversion to sort of, the models are all performing a form of reversion to a mean, but the point is that the model from STOPS is much better able to capture the full dynamics than the other 2, which are simply trying to smooth it out. And it can summarize the same thing by applying the same sort of model. So these, and again, the models that I'm building here are just a standard neural network package implemented in Python, applied to each of these algorithms, each of these embedding strategies in the same way. And what we see is that the performance of the models does depend in a strong and significant way on the embedding lag that I choose. At least MDOP does worse for Lorenz, and appears to do somewhat better than the other two on the Lobster, albeit with a longer tail and outliers than the other two. So the bar here is mean, standard deviation, and everything beyond 3 standard deviations from the mean. So the stops technique with the embedding lags I'm suggesting here either builds a very good model or a very bad model. But the important point is that it has the capacity to build better models because it's embedding the dynamics in a better way. Okay, so I've only just scratched the surface in terms of what we want to do with these embedding techniques. We're currently working on building these embedding methods into techniques to build models that are able to detect tipping points and other transitions like that in experimental data. So the idea there is that we have, and the data that we're working with is actually from ECG going into heart rhythms going into fibrillation, and we want to build models that detect the onset of the fibrillation as early as possible. And we're finding that, again, much like the Lobster neuronal data, this is noisy experimental data with multiple different timescales. The standard methods just don't quite do it, whereas trying to unravel the loopiness at all different scales allows us to build models with those different timescales involved in them, which are better at prediction. The results that I presented you here show that this technique maybe gives us slightly better performance. Certainly nothing that is definite, but it does offer a more explainable method of constructing embedding lags in that the technique is directly building on the geometry of the attractor that we're trying to untangle. So finally, I will acknowledge that a lot of this work has been done for specific applications in industry. We're doing some of this with, as I mentioned, looking at geological modeling with companies such as Anglo American, where they're looking at geological prospecting, working with other industries in WA, Roy Hill, BHP, Alcoa, in applying these tipping point methods for regime change. And that work is funded through the Australian Research Council research centres that are listed down the bottom of the screen. So finally, I'll finish by going back to this paper and the reference for this paper. All the references to all the techniques that I was talking about are contained in this, as well as the full details of the new method. And I'm happy to take questions if there are questions, Sanjeev.
Yeah, thank you very much for this very interesting talk and very concise. And also, I guess I'm very highly motivated to read this paper which you're showing. There are some questions already. Can you see them in Q&A box?
Yeah, I can see the box. Okay, so let me see, what have I got?
Already 3 questions.
Yep, I'm just trying to work out which one do I go for. Which one's okay? So Narayan was first. Most dynamical systems are spatial temporal and hence need measurements, typically multi-channel. So the honest answer: how do these embedding theorems deal with multi-channel data? Everything I've talked about was a measurement function which is just single univariate. The honest answer is that generally they don't deal so well with the multi-channel data because it's an additional complication. But having said that, these methods that are looking at non-constant embedding lags do offer a way to extend it to multi-channel data. So just as we are choosing different embedding lags, one could imagine choosing from amongst the different channels that you have available to you. Yeah, in the real world, this happens a lot, and it's also not just multi-channel data, but also you may get different measurements of the same system that are actually measuring different sorts of things at different timescales. So how do you combine fast and slow variables that are being measured differently from the same system? There's a lot of problems here that need to be developed that haven't been developed and need more work. So my answer is that, yeah, it's a good question that hasn't been answered. The second question, can phase space perform with certain with a certain objective criteria and perform well for different. Okay, so I think the question is about whether a single method is going to work well for every time series, or whether you just get different methods that work well for a different time series. And I think that's part of what we're aiming to overcome here, because a lot of the embedding methods, like a lot of data-driven techniques, people develop a new algorithm and show that it works on one particular thing better than everyone else's, but maybe without the generalization that you would expect. So we're hopeful that methods like this are actually quite generalizable, in the sense that they work well for the standard systems, for the standard Lorenz system. They work as well as the other methods for basic test cases like sum of signs. And yet they also work well for more tricky examples, which is what we're showing with the spiking neuron data, where we have dynamics that is more complicated. Every single one of these techniques, though, is in some respect ad hoc. This is a rule to do something because we think it works well. The theorems themselves say that it doesn't matter. Any lag will do generically. And what we're trying to do here is choose lags that somehow perform better. And that's always going to be subjective. It's always going to be a little bit ad hoc. So you're never going to get a perfect embedding method that can work free of operator discretion, I guess. Does that get to the question? Jaish, are you out there?
I think
Yeah.
They cannot speak.
Okay.
I think you can move to the next question.
Okay, and so the next one is Joshua, but it's not, it's Liz. Okay, so Joshua Garland, but actually Liz. I think I missed how you use the significance curve, not just the highest peak, obviously. Yeah, so the significance curve, if I just go back to one of these curves here. So this is the Lobster one. And so here we were actually selecting the lags which correspond to the peaks in the significance curve, right? So for reasons which kind of escaped me a bit. So what was that? So we're looking at the points, the peaks in the black line, and trying to identify lags corresponding to those peaks. So the heuristic is basically, we're looking at peaks. Now you said chosen the one near 500 on slide 20. I guess 21, one of these 21s. And possibly is this, yeah, this peak here. Yeah, so we do have an issue that the significance measure does get blurred out a lot for very large lags, where the value of the lag is so large, it doesn't make sense. In fact, what's going on here with the Lobster is that the small lags, small peaks correspond to the fast behavior. The big fat peak at 500, that corresponds to the slow quiescent stuff. So we want both these time scales. Right, so the little bumps early on, they're the fast stuff, and the big bump at the end, that's the slow stuff. So if we look at the lags that get chosen here, there's one at about 500, And there's one corresponding to one of the short bumps as well. And there should be another one there somewhere, but it's not showing up. Whereas the other methods just show the two larger lags. I think that's, I guess, Liz, you can have a second go if I didn't quite get that right. Jim, can you address the advantages and disadvantages of increasing the number of delays using smaller delays? So do you mean having a large number of small delays and increasing the embedding dimension versus a small number of larger delays and a lower embedding dimension? I've got Jim, you've raised your hand. Does that mean yes?
So you can unmute and answer the question. Currently you're muted. Can you unmute?
Jim, are you out there?
Connection is gone. Yeah, maybe you can move to the next question because the connection doesn't seem to be on.
Okay. Well, yeah, the rest seems to be the answers to the question. Okay, so yeah. So Narayan's second question is about the computational cost of persistent homology calculations. And the answer is a lot. Topological data analysis is getting popular now because computers are finally at a stage where we can actually do some of it, but it's still very computationally intensive. So, so the technique I'm using here, I'm just looking at single strands. So when I'm doing the topological calculation, I'm only calculating the topology for a set of points corresponding to one orbit. So that's not too onerous. But if you wanted to, as I do, calculate the persistent homology over an entire attractor, that becomes extremely expensive. Excuse me. There are ways to get around that. People are working on techniques either in terms of sampling, downsampling the data so that you can estimate your quantity by just taking a subset of the points. Or the other thing that people are working on is the stage that I described where you're growing the balls around the points to get the edges. This is called filtration, and there's several different schemes for doing this, and that's where a lot of the computational cost is. So they're working on ways to make that easier. I can see Jim's hand is back again. So if I click on that, does that allow him to speak?
I finally found my voice.
Yep. Okay, we've got you. I can hear you.
Yes. Very interesting talk.
Thanks, Jim.
But you seem to be emphasizing how to choose a specific number of delays.
Yep.
Without addressing how many delays should you have.
Yes.
I mean, the advantages.
So yes, I've completely ignored, well, almost completely ignored the problem of embedding dimension, like how many lags should you have?
So one way to address this, could you address the cost of doubling the number of delays?
Yes. So, okay, first of all, there was one of the things that I skipped over was this local linear modeling idea here, which actually directly has a way of measuring cost of additional delays. So what we're computing here is, so we're trying to build a linear model from a set of delays L0 up to Lm minus 1. There's m of them, but the first one is 0. And my heuristic is that I want the delays to be a good model to predict the next coordinate. And my criteria for a good model is going to be based on this idea of description length, which essentially is a model cost. And the model cost depends on the number of parameters in the model. So the more parameters, and the parameters here are directly related to the lags, the more lags I have, the more costly my model. So does the addition of another lag actually give my model sufficient additional explanatory power to warrant that lag being in the model? The calculation of this is essentially based on a data compression algorithm. So if I want to communicate the time series to you, is it more compact to communicate the model prediction errors with the additional model parameters, or communicate larger errors with fewer parameters? So this is one way in which you can actually get a direct trade-off between the additional lags. Each of the other algorithms that I talked about has built into it some heuristic, which essentially just stops choosing additional lags when you've got too many of them. And usually this comes down to either I only expect the system to be 3 or 4 dimensional, so that's all I'm going to build, or I simply don't have enough data to build an embedding which is higher dimensional anyway. And as you pointed out to me earlier in this week, if you have too many, if you embed in too high a dimension, then you're going to see all sorts of interesting, spurious things coming out of your estimation of invariance. Does that get halfway to answering your question?
Yes, great.
It is a important problem which is not very well addressed with a lot of the methods. I guess the false nearest neighbors type approaches are the way that people would usually heuristically deal with this. And that kind of takes account of the noise and the amount of data issue. But again, you've got to look for a plateau, and a plateau is a difficult thing to define.
But I think Lobster problem looks impossible.
The Lobster data is fantastic. It is really beautiful data. It's a beautiful data set because it's got so much going on. And it's the way in which you've got this long, slow loop, comes back in, injects itself into this little fast thing, and it goes whizzing around that, and then it starts slowing down and then just falls out again. It's fantastic. I don't really understand the details of the experiment they did, but yeah, it's a fantastic data set. But yes, quite a difficult one to model. Okay, so I talked about Marianne's question about the persistent homology computation. Okay, so I've just realized I should be clicking that I've answered these questions. Abdul, is there a method which is based on some rigorous mathematical footing? Yeah, so I kind of, as I said before, each of these is based on a heuristic of sorts. And the issue, I guess, in part is if you want a rigorous mathematical reason for choosing a set of embedding lags, then if you're going to build on the embedding theorems, then first of all, the embedding theorems require that your observation function is continuously differentiable, which is problematic if it involves a digital machine at a technical level. And also, basically, the mathematical results simply say that, well, any set of embedding lags, provided you have enough of them, and the conditions on each of the theorems says how many, what the dimension is that you need to go up to, provided you have enough of them, then that is adequate generically. And generically here just means that you can make an epsilon perturbation to your observation and it will work. So all of the things that are not going to work are very close to things that do work. So the fully rigorous approach is, well, anything works. And everything else that's being built on this is just heuristic choices that for practical data will work better. So there's always going to be some situations that work better than others and some tricky data like this Lobster data set that just are very, very hard to deal with. I'm assuming that if I don't answer the questions, I'll just get asked more questions further down this list. So I'll just keep moving and see how I go. Narayan again, the biological data is often determined by frequencies that overlap the signal of interest. So the question is whether or not, so if you have biological data, you may get something where your time series is contaminated by some other frequency, by power line noise or by an extraneous beat that is not your signal of interest. And can the topological data methods be useful to get rid of that, more useful than spectral methods? I don't know that there'd be, I don't know. I suspect yes, but I suspect yes on the basis that just taking a notch filter to get rid of a frequency you don't want can be kind of dangerous if you're dealing with a nonlinear system, because you really, yeah, the spectral methods can be a bit, can do dangerous things to your data. So I would like to see the topological data analysis methods do more. I'm not sure, given the computational strain that those methods would have, I'm not sure exactly how you would do that. Possibly by looking at a short section of this sort of data, you could build a more topological filter to get rid of that frequency. I haven't thought too much about it, but I think that's probably a good idea. Can we use delay embedding for spatiotemporal data, which is already high dimensional, but still low dimensional compared to the total degrees of freedom? Not quite sure that I understand the question. Jayesh, are you there? Can you speak?
Hello, can you hear me?
Yeah, I can hear you. Yep.
Yeah, so my question is, let's say we have experimental data, which is we are capturing, suppose the images from the experiment.
Yep.
But it is still not capturing the full dynamics, let's say, happening within the system. So the delay embedding tries to reconstruct the full dynamics. So is there any way, or can we use this delay embedding to get like recreate the dynamics that is we are lacking because we are taking only few measurements, or let's say we are taking only image which is 2-dimensional, but the dynamics is happening in 3-dimensional space. So can we use some of this technique to get like more involved dynamics out of the data?
You can. There's issues involved if the system that you're looking at is actually infinite dimensional, if it's a delay system, or if it's a fully spatiotemporal system, so your state space is actually infinite dimensional. That is problematic. I believe there are extensions to the original embedding theorems for that case. I don't know the details offhand, so I don't want to answer that exactly, but I believe people have looked at that. From a computational data analysis point of view, you can certainly go a long way to do that, especially if you're looking at sort of spatial temporal systems that have a lot of spatial correlation. Afraid that's the best I can do to answer that one.
I think like we might can get some like patterns out of the image and also think of those time series and try to get delay embedding of how the extent to which these patterns are present. That might be low dimensional and then go to high dimensional by using delay embedding. Might
Yeah,
work.
yeah, that could work too. And the other thing, I guess, is if you have, if it's a spatial temporal system, but if you've got a lot of spatial heterogeneity, so the equations are basically the same everywhere in space. That would certainly help, I guess.
Yeah. Right.
And I guess I look at Jenna McDonald has got a similar question, I think. Yeah, I'm afraid my answer to that is I don't know. So the question is, again, about spatial temporal data. And if we choose to find embedding for each spatial dimension individually, so if we can observe different spatial dimensions and we embed each of them individually, do we average that? Or do we find lags that are most common amongst all of them and use those lags across the whole thing? I would suggest, or I mean, I'm just guessing, but I would suggest that if you built separate models of each spatial dimension separately, you would end up with a very high dimension, and you add that all together, you've got a very high dimensional embedding, which you could then probably do some sort of projection. So you project down from that very high dimensional space to a lower dimensional space, which is closer to what you want. And that might reveal commonalities amongst the embedding lags, or it might actually not do that at all and just give you something different. I don't know. No, that's a really good question that I don't have a very, very good answer to.
That was good. Thank you.
Yeah.
I'm curious, would you suggest dynamic mode decomposition and stuff such like that? I mean, have you used any of those kinds of decomposition methods in order to be able to reduce the dimensions and seen success, or?
Yeah, so either dynamic mode decomposition or even just principal components, any of the projection techniques. There's actually some work that I did with a postdoc, Leo Portes, which we published in PRE recently, which we used a slightly different projection technique specifically for genetic data. So there you've got very, very high dimensional data. And it was essentially a kind of nonlinear extension of PCA, which allowed us to extract gene expression profiles corresponding to particular expression patterns. I can give you the reference if that would be
great.
helpful.
Thank you.
Okay, I think you have answered everything. I don't know, any of the panelists have any questions?
It's still not quite my bedtime yet, but
Yeah, Professor Ampi has a question. Yeah, go ahead, Professor Ampi.
See, I was wondering towards the end, it's a very interesting talk, but towards the end, you were mentioning about looking for tipping or dynamical transitions based on data.
Yep.
So normally we do a sliding window analysis or a rolling window analysis. And do you recommend that for each window, you take the same delay, or for each one you separately find out a delay, because the results can vary based on this. So what would you recommend?
so
Use the same value?
Yep. So the way that we're doing it is essentially as you described. So you have your historical data, you build a model on that historical data, and you slide that along, and you wait until you see the new data not conforming to the model.
Yeah.
And that's then you've now moved away from the old model. So we have a fixed embedding for the old model, for the learning state, for the old state, and that's got a fixed embedding, and then we expect things to change, and all we're looking for is a breakdown of that old model. Just for the particular systems that we're looking at, the choice of embedding was rather subtle, so we found that these techniques actually needed to be used to capture the different timescales. But you
Okay.
could imagine something with update as well, where you progressively change your embeddings as you go. But we're not doing that.
Okay.
Does that make sense?
Yeah, so you are suggesting you keep the same delay in all the windows?
I'm saying that's what we're doing at the moment. There may be reasons for doing otherwise, but
Yeah, I was also, I mean,
but
that's
for
basically what we normally do. So
Yeah.
I was just checking. Yeah,
Yeah.
good. Okay, thank you.
I think the audience has tired you out with a lot of questions, but yeah, and all the questions. So I want to thank Professor Small for his very interesting talk. And we will take a break in summer, so there will not be any talks next 3 months, and the next one will be in September. So stay tuned and enjoy your summer.
thank you.
very
Thank you for the
Okay, thank
invitation, and thank you for the great questions.
much. Thanks for staying extra late.
Bye.